Hello children, now we are going to prove one of the most important theorem, rather conclusion, that square root of any prime number is an irrational number, but we prove it by using an example. So the question will be asked, has been asked several times in the previous examination. So almost every first term examination has this question. Prove square root of any prime number. Here I have written 5. It can be square root of 2, square root of 3, square root of 7, etc. Okay. So let us start with this. Square root of 5 is an irrational number. Okay. We prove it by method of contradiction. What is the method of contradiction? Whatever we have to prove, we start with opposite supposition of that. We want to prove that it is an irrational number. We will start with the supposition that suppose root 5 is a rational number, and therefore it is the first line. Suppose root 5 is a rational number, and we know that a rational number can be written in the form of p by q, okay, where p and q are integers, and we are assuming that they do not have any common factors. Common factors are there, they are cancelled, and then this is the simplest form. They do not have any common factor. This is underlined because you get the contradiction to your assumption. So this is your assumption that they do not have any common factor. So root 5 is equal to p by q. Cross multiply, you get root 5 q is equal to p. Squaring, you get 5q square is equal to p square. Okay. So p square has a factor 5. That is what I have written. 5 is a factor of p square. But just now we have studied a conclusion that if a number x is a factor of any another integer, then that number is a factor of the square root of that integer also. So here we said that 5 is a factor of p square. So 5 will also be the factor of its square root, that is p. So that is what we have written. 5 is a factor of p. Now p is an integer and 5 is the factor, so p can be written as 5 multiplied by some number because it is a factor. So if it is a factor, it will be there in the factorization. Okay. So p is equal to 5 multiplied by some another number. Okay. So 5 is a factor of p, and using that conclusion we have written suppose or let p is equal to 5k, where k is some other integer. So if I square this, I get p square is equal to 25k square, and then I get a link. Okay. 5q square is equal to p square and p square is equal to 25k square. So this is equal to this. A is equal to b and b is equal to c. Therefore a is equal to c. So from equation 1 and 3, we reach to the conclusion that 5q square is equal to 25k square. If you transfer this 5 in the denominator, you get 25 upon 5 is equal to 5k square. You are getting a similar equation. What you are getting here, a similar equation you are getting here. Q square is equal to 5k square. In other words, 5 is a factor of q square. 5 is a factor of q square. Again, I am using the same conclusion. If a number is the factor of another integer, then it is a prime number is a factor of another integer, then that prime number is a factor of the square root of the number. So 5 is a factor of q square, therefore 5 is a factor of q. Now I have given number 4 to this equation. Here I have written 5 is a factor of p, equation number 2, statement number 2, and here it is statement number 4. If you combine the two statements, what do you come to know? 5 is a factor of p, 5 is a factor of q, that means 5 is a common factor of p and q. So we have written from 2 and 4, 5 is a common factor of p and q. That means p and q, they have a common factor, but here we said that they do not have a common factor. That means whatever conclusion you are getting is contradictory to your assumption, is saying that your assumption is wrong. You are reaching to the wrong conclusion. You are reaching to the wrong conclusion. What is the conclusion? That 5 is a common factor of p and q. And in the beginning you said that they do not have common factor. That means you are getting the wrong conclusion. Why you are getting the wrong conclusion? Because you started. This contradicts the assumption. This is the assumption. No? Why you are getting the wrong conclusion? Because you started with the wrong supposition. What is the supposition? Root 5 is a rational number. Okay? Therefore, our supposition. What is the supposition? Root 5 is a rational number. Is wrong. It is a rational number. Is wrong. So if it is not rational, then it is an irrational number, and therefore we reach to the conclusion root 5 is an irrational. Now the same way, in the same way, you can prove root 7, root 11, root 13, root 17, root of 29. Any prime number you can write here as a radical and rewrite the same proof. So I have given you 4 different square roots of prime numbers. You can write a similar proof there using the logic which I have given to you. Okay. Now let me remind you that this proof has been asked almost in every examination of previous years. So it is equally important for you. Okay. Thank you, children.